Ina nei ka huri tātou ki te kai kōrero tuarua o tēnei kaupapa, the second talk for the Risk Assessment and Ecosystem Impacts Research theme, Malte Cordes. And the talk title is Capturing Forest Structure with High Density Laser Scanning. A team at Scion are developing world-leading methods to capture and analyse dense three-dimensional colour scans of complex forests. Malte Cordes, a visiting MSc student from Germany, is currently working on scans collected at Cody monitoring sites in the Waitakere ranges. Malte will describe the technology and its potential to monitor forest dynamics, illustrated using the hot-off-the-press results from the Waitakere sites. Tēnā koe, nau mai, whakapiri mai, whakanuku.
Kia ora. My name is Malte and I'm a student from Germany, and I'm working on laser scanning data in collaboration with Scion in order to assess the structure of kauri forests. And just a quick introduction, what is laser scanning or how does it work? So the scanner emits non-visible light pulses which reflect at the surface of an object and then turn back to the scanner. And based on mathematical processes, the location of the point of reflection is stored as a point in three-dimensional space. This results in a point cloud, which is covering the surface of objects, and in our case, vegetation. A laser scanner can be carried on aircrafts or on drones, can be carried on vehicles, or in our case, in a backpack. And this is a very quick and easy way to record huge data sets which can be used to measure vegetation attributes like diameters or heights, or also to extract the ground surface, for example. We conducted laser scans on the same sites as mentioned before in the Waitakere ranges. We covered different development stages of kauri forests and also kauri diabetic symptomatic and asymptomatic areas. And to ensure a sufficient coverage of vegetation, we walked on a predefined grid. And by that, we covered an area of approximately 2,000 square meters in less than 1 hour. And this produced a 3D image, a point cloud, containing around 450 million points. On the lower left, you can see a point cloud of a recently conducted scan in the Cascades. And on the lower right, you can see an extracted tree which died due to kauri dieback and show quite good the loss of foliage in the canopy. My work's focus is on the forest structure and natural and anthropogenic disturbances, climate, the tree species composition, and their size and distribution have an influence on the structure of forests. And these structures can be described by different metrics, which, for example, addresses the height or the openness or also the complexity of forest stands. I had a closer look to these metrics. I wanted to see how they react to the structure of kauri forests, and I found 4 promising metrics which can describe changes in this forest type. And these are here to see in the figures D, F, G, and H. These are the vertical complexity index, the height of the maximum vegetation density, the porosity, and the canopy rugosity. So the applied technique showed a very efficient coverage of the forest vegetation, and the selected metrics were unfortunately not detect changes caused by kauri dieback at one point in time. But the testing what I did has identified metrics which will be suitable to detect changes if we repeat the scans at the same locations at a second point in time. The data has a huge potential for further analysis and it creates the baseline for following scans. We can create accurate tree maps or even have a closer look at individual trees. And it is possible to link this data to other data sources, like, for example, the ground and field measurements, which were mentioned in the talk before, or also to satellite images or aerial laser scanning. And there's even potential for new modern technologies like VR technology or the use of artificial intelligence algorithms. Kia ora.